Hello everybody and welcome back to the channel. I hope you're all doing well. I'm going to try and make my way through this video pretty easily, but it might be a little bit tough for me because I have yet again contracted a cold. I think I've been kissing the homies goodnight a little bit too much, but soon I am actually going out to go ahead and try and kiss some ladies goodnight. That being said, if you've been taking the under on the Jordan 0.5 ladies line through all of 2023 and the beginning of 2024, you might be a billionaire. So yeah, with that being said, let's get into this video and I can stop talking about anything else. All right, ladies and gentlemen, so today we are crawling the web. What does that mean? Well, in practice, this is something that a lot of companies have to do when they want to gather a large amount of openly available data, whether that's to build a search index like Google or a large language model like OpenAI. There are a variety of reasons that we might want to process all of the information available on the internet. That being said, that doesn't make it a trivially easy task. In fact, it's actually quite hard. So let's go and talk about how we might do this. One example, if we're just looking right here, is let's say I start out with Wikipedia. Wikipedia might have a link on it that leads me over to the New York Times, and the New York Times might have a link on it that leads me over to my own OnlyFans. That would be tragic. Let's hope that never happens. So, assuming that we know all of these things, we can go ahead and crawl from site to site. They should all be linked together, right? At least at some point. So, with this in mind, let's list out some problem requirements. Okay, so we've got 4 here. The first is that we need to be able to scrape all of the content that is currently accessible online. The second is that we have to store all of it. Again, this stage is kind of optional depending on what you're doing, right? If you're OpenAI, you're going to be using this as some sort of training data. If you're Google, you're going to be building a search index. I don't really care as much about that particular step. That is more specific to your own domain. I just care about actually crawling the web and storing the contents. Number 3 is that we have to respect website crawling policies. So if you're not aware, we have these things called robots.txt files. Those are per host on a website, meaning like Wikipedia has a single robots.txt file. And it basically says, if you're a bot crawling my site, here's what you can do, here's what you can't do. You don't want to violate those, it's not right. Number 4 is that we want to be able to complete this process within a week. Now you might say a week, that's a ton of time. Well, guess what? The web has a ton of data. It's not that easy to just crawl it. We're going to need a lot of computers probably to get this done. So let's estimate how many computers we might actually need. Well, for starters, if there are around 1 billion web pages, and I did Google this, though that being said, there might even be sub-web pages, and this estimate could be completely off. It's hard to say. And let's imagine that each web page is itself around a megabyte. Another number that I Googled, so again, could be completely off. And if we have to make 1 billion requests where each one is a megabyte, that means that ultimately we're going to have to load in and store at least a petabyte of data, besides whatever, index or model or anything like that we end up building. Additionally, let's say we have a week to do this. That means we have around 600,000 seconds. And if we have 600,000 seconds, it means 1 billion requests divided by 600,000 seconds is about 1,500 requests per second. Now that is obviously a lot. I would say, in my personal experience, just using my own internet, it probably takes me about 1/3 of a second to load a web page. I think that's semi-reasonable. So maybe we need 500 different threads loading web pages at a time. If we did, most modern CPUs have, 4 cores, 8 threads, if they use hyperthreading. So maybe we need, around 100 servers if we want to devote a decent amount of CPU usage to this. I think that's a reasonable enough number, and that's what I'm going to stick with. Obviously, these numbers are going to be wrong. They're pretty crude estimates, but I think this is how you might go about doing a capacity estimate for this problem. Okay, the next thing we're going to do is actually go over the process of web crawling, because it's not overly intuitive. There is actually a decent amount that you have to think about here and do. And so the point here is that once I go through this list, we have to think about which of these items we can actually optimize and improve in order to make this process as fast as possible. So the first thing that we do, if we're one of the threads that's actually going ahead and doing our web crawling, is that we have some sort of list, which I'll dub for now the toCrawl list, but we'll rename this in a little bit. So imagine this is just some list. It doesn't really matter what the ordering is. I know there's a URL that I have to crawl. I'm going to pull it from that list. The next thing that we want to do is check, have we already crawled this? We don't want to do duplicate work. That's just going to waste time. The next thing that we want to do is check if crawling it is compliant with the robots.txt file. So if the robots.txt file says, hey, don't crawl this, we don't want to crawl it. If it says, hey, only crawl this every hour, and we crawled it 20 minutes ago, we don't want to do it again. So for example, if I was at like twitter.com/a, and now I want to crawl twitter.com/a, /B, but it hasn't been long enough between those two crawls. I have to wait a little bit before I do that. And so we want to do that in a smart manner. Another thing is that we actually have to get the IP address of the host via DNS. Something like twitter.com/A doesn't actually mean anything. It has to resolve to some IP address, something like and we have to get that from something called a DNS server. Now, a DNS server is probably not just one server. In reality, that itself is a distributed system, but we have to figure out what the IP address is at the end of the day, and when we do so, then we can actually go ahead and jump over to that server and fetch its contents. Another thing that we have to do is, once we know the IP address, like I said, we fetch the contents. That is in and of itself an HTTP request, and it is going to take some time. Additionally, now, once we've loaded the content of that URL, we have to check if we've already processed identical content from another URL. So this is actually something that's apparently pretty common on the web, is that two URLs with completely different domains actually go ahead and store the same physical content on them, like the same exact HTML file. And if that's the case, it's going to save us some time if we don't store it again. Next, we have to parse the content. If we're Google, that means indexing it. If we're OpenAI, that just means, probably storing it, and then we'll have to, iterate over it later when we're doing training. Again, store the results somewhere. That's probably going to be in either an object store or a distributed file system. And then last but not least, we have to take all of the URLs that this HTML references and put them into our to-crawl list. So hopefully that makes enough sense. It's not too hard of a process. It's clearly one that is a bit recursive. So let's go over how we can make this thing as fast as possible. And the way that we're going to start this is by actually pulling from our quote-unquote to-crawl list. So the question is, if we have this to-crawl list, which from now on I'm going to call the frontier. If you are familiar with graph traversal algorithms, the frontier is basically the next set of points that you want to traverse. So again, we have this frontier of URLs that we want to traverse. How can we reduce the amount of time that it takes to fetch a URL from it? Well, if every single node that is processing, so if this is node 2 and node 1 is on the left, if the frontier is stored locally per node, that could make crawling very fast, because then we can basically get a next set of links and just hold them locally without having to make any RPC calls. So that is going to be fast. However, it is also going to have some downsides. So even though it's going to be faster, right, because we avoid an extra network call when actually having to go ahead and adding things to the frontier, at the same time it has some big downsides. So the first is going to be there's no load balancing, right? If I happen to have a seed URL on one node that leads to quite a few more traversals than on another node, the problem there is that they're not going to do equal amounts of work, and one of them might actually go ahead and be idle. Now, we never want any of our nodes to be idle. We want all of them to be cranking at full capacity until everything has been crawled. Another thing is that we can process duplicate links. So if node 1 over here on the left says, hey, I'm going to process Twitter next, and node 2 on the right says, hey, I'm going to process Twitter next, they're both going to process Twitter, they're both going to store Twitter. We don't actually have to do that. Only one of them has to do that, and now we're doing duplicate work. And so if we didn't want to do duplicate work, well, how could we avoid that? We could have some sort of centralized database, DB, like how I am, I'm down bad. And this centralized database would basically go ahead and allow us to check whether or not we've already processed the URL. That being said, that is going to take some time, because now we actually have to go ahead and do a network call to read from the database. And so that can be kind of slow. How can we avoid doing something like this? Well, what if we actually made our frontier distributed, right? So when we find a URL, we're not necessarily holding it locally, but more importantly, we're actually sending it over to other nodes. So this is going to accomplish a couple of things for us. But the first and most important is that this way we can make sure, by having a load balancer in the middle, that basically we can make sure that each node is getting a relatively equal amount of work. So the load balancer could do something like round robin, at least naively, to make sure that all of these nodes are going to be processing similar numbers of URLs. So the next question we started to touch upon before, which is how can we avoid duplicate fetches? So if we see the same URL, if we've already processed it before, how can we avoid processing it again? Well, one solution that we already discussed is some sort of centralized database. And this works, it's doable, but the issue here is that now all of a sudden every single one of our nodes is going to have to query that database. And if that database is over the network, that's not so easy to do. It can actually take a decent amount of time. So what if recall that I basically suggested that we do some round-robin partitioning up here in order to route requests. What if we did something a little bit smarter than that? Well, the idea is that what we could do here is actually partition our nodes by the URLs that they're willing to process, right? So we are doing a basically partition by hash range of potential URL. So if X and Y are URLs, they will go to the same node if they are equal. And that way, now what we can do is cache some local state on every single node, saying here's a list of URLs that I've already processed. And so if they find that an incoming URL says, hey, twitter.com/a/b is incoming, they're going to say, I don't need to process this, I've already done it. And so that way we have this already cached table. And so if we're already sending these URLs around, now we can avoid an extra networking call by doing this. Additionally, because hash range should distribute relatively equally, because it's pretty much random how hashes work. If it's a good hashing function, it should distribute our range nicely. Then this should also keep our load relatively balanced on each node. So another question is, well, how can we actually avoid duplicate content on different sites? So I mentioned a common phenomenon on the web is that basically we have duplicate HTML under different URLs. And so the issue here is this is a little bit less simple, right? So the first thing that we have to actually do is fetch the content first, which is expensive. Then we have to take a hash of it. So we have to do some sort of method that takes a hash or a fingerprint or anything that uniquely identifies this content so that we can quickly check across nodes basically whether we've already seen this piece of content. And the problem with this approach is that since we've already basically seen these, or rather since we haven't seen these hashes before sending the URLs around, there is no way for us to effectively smartly partition our nodes such that two different URLs with the same content are going to be processed by the same node, right? So if you're thinking about what I'm saying here, we only have the ability to know what the name of the URL is at the time that we send it to another node to the frontier. And so since we don't yet know if its content is going to be this or that or anything else, we can't partition based off of its content. We can't partition based off the hash of its content. Unfortunately, we just have to bite the bullet here and get the hash of that content once we've already fetched it. And so the question is, well, we're going to have some sort of centralized way, or maybe a decentralized way of actually checking whether we've seen this hash before. So how can we do it? How can we make this fast? Because otherwise we're going to have to be sending a lot of network requests around, and we want to make those not heinously slow. So this is what I would dub content hash checking, and I will discuss a couple of different approaches here, and you individually can evaluate which one's the best, but I think that all of these are valid. We would have to do some benchmarking to really tell how much of a difference they would make. So keep in mind that let's imagine we have something like a 64-bit hash of every single piece of HTML. We have a billion sites. That means that basically we now have up to 8 gigabytes of data to store if we want to store the entire set of possible hashes. And potentially even less than 8 gigabytes, right? Because there may be duplicate hashes, and then that data set size would decrease. So considering that 8 gigabytes is actually pretty small, in theory we can store this entire data set on one node in memory. And so that is actually a pretty practical solution, right? If we just had some Redis instance, we could store all of our hashes there. The reason I say Redis is we want to make this thing as fast as humanly possible, and Redis, using basically a hash map, is going to allow us O of 1 lookups in memory. And of course, if we want to make sure that our system is fault tolerant, we can also have a replica over here. We can just update that one asynchronously in the background. And so as a result, if we're always reading from and writing to the leader, we can maintain strong consistency. Of course, if the leader does go down, we may lose some writes on the replica. And as long as basically our processing is idempotent, right, then it's not a huge deal if our replica is a little bit behind, because so what, we'll process a couple documents 2 or 3 times, and it's not a huge deal. Then our replica will be the leader and we'll be good to go again. So again, idempotency is important here, but we can continue to talk about different solutions. So I would call this one the centralized solution, right? Because we've got one database that is the source of truth. It's strongly consistent. We can rely on it, and it should be hopefully pretty fast, depending on how close these nodes are together. If this node is in the US and this node's in India, at least one of them is probably going to have slow requests over to that Redis instance. So if that were the case, what could we actually do to speed things up? This would be a case where, our processing nodes are possibly in multiple data centers, and those data centers are pretty geographically far apart. So again, reading and writing to one single instance of Redis will be slow for at least a subset of our processing nodes. So another idea would be to actually use like a decentralized set CRDT on every single node. So for those of you who don't really remember too much, this means a conflict-free replicated data type, which effectively means that we are using some sort of multi-leader replication. We're maintaining a set on every single node, and then in the background on a separate thread, we're performing an anti-entropy process whereby all of our sets are eventually consistent. Like if we did nothing to them, they would converge to the same value, but it would take a bit to actually do so. So the point is here, because these are eventually going to converge with one another, it is possible that two nodes might actually process URLs that are different but have the same content. But again, if processing that content is idempotent, meaning it doesn't matter if we process it twice, it's just a waste of time, then this isn't a huge deal. It's possible that the occasional duplicate processing of a document will actually be better than if we have to hit a Redis instance in the middle of everything every single time. And so what that would look like is, imagine we have node 1 over here, node 2 over here. Their starting state is, this guy processes a document that hashes to 1, this guy processes a document hashes to 2, this guy processes 3 and 4. They don't actually have to know about each other instantly, but eventually what will happen is that this guy will store 3 and 4, this guy will store 1 and 2, and so eventually if those documents come along that are duplicates, hopefully we can detect that and then not process them again. So again, this all kind of relies on the fact that these operations are idempotent and whether it is actually tolerable if we do process the occasional duplicate document. If we can, this may actually be a better solution for you. It really depends what percentage of the time we'll have to be processing the duplicates, and as well, how fast we could reach out to a potential Redis instance. The next thing to actually talk about is domain name service, or DNS. So as I described earlier, DNS basically is giving us a mapping from a host name, something like Wikipedia, to its actual physical server IP address. And so this is going to say now we can reach out to the IP address to go ahead and get us the content that we want. So the thing with DNS in general is that if we're talking about the entire World Wide Web, this is probably going to be too large to just cache it on all of our nodes. It's not changing a lot, or rather it's not changing too much, so in some senses, in theory, if it was super small, maybe we could actually cache the whole thing. But in reality, it's going to be pretty big. There are a lot of websites out there. So typically, this is going to require a network call, and the question is, how can we actually go and make this faster? Well, one important thing to remember here is, like I mentioned, DNS is going to be on a per host basis. If I want to get an IP address for wikipedia.com, that's just going to be one thing, which is great. Maybe it'll be a few, but the point is that it is stored, those entries of IP addresses, per host. And so basically, previously, we said to ourselves, hey, if we have twitter.com/a, that's always going to be processed on node 1. But what if instead of doing that, we just said twitter.com/anything, so /*, that's going to be processed on node 1. Now, instead of partitioning on the URL itself, what we could actually do is partition on the host. So the question is, what benefit does this actually get us? Well, the biggest thing is that now, per node where we're doing the processing, we can actually maintain a cache. And again, it's possible that all of these entries for DNS are going to be too big to hold entirely in our cache. But considering the fact that websites tend to link to themselves, it's most likely going to be the case that, if I get twitter.com/a, it's likely going to link to twitter.com/b. And so being able to have recent DNS requests cached on our server could be super helpful for us. We can always just use an LRU algorithm, so eventually when we do run out of space, we just get rid of the least recently used entry, and hopefully that should save us a decent amount of network requests. So now, again, what I said is that everything from Facebook will be on the same node as opposed to just one specific page on Facebook. The next thing to consider here is actually going to be the robots.txt file. We mentioned that what this basically does is tell us what type of crawling rules that we have to follow to be compliant with that website. And so again, keep in mind that based on our last slide here, we're now basically partitioning all of our processing nodes based on their host name. And this actually is going to come in really handy as well for the robots.txt. The reason being that robots.txt is not per website page, it is also per host, right? So again, we can do the same thing that we did with DNS and keep a local cache of the crawling policy. Again, this is super useful because websites tend to link to themselves, or rather they tend to link to other pages within the same host. And so one example of what a robots.txt file might tell us is basically say, hey, if we're on Twitter, right, my robots.txt is saying don't crawl this particular link. And so now on a node, I'm right here, I see Twitter. I already have this thing cached, right? It says don't read. And now guess what I do? I don't read Twitter, I move on to the next URL. Seems easy enough, right? A second example would be, hey, you can only crawl Twitter once per minute. So let's say on this site, I crawl twitter.com/a, and now I say, oh, you know what? I called Twitter at 8 o'clock. So now twitter.com/b comes in. And now we're going to say, oh shoot, you know what? We actually just crawled Twitter, so we're going to have to wait for a second. Rather than just waiting in a blocking fashion where we wait and don't do any other work, what we should do is take /b and put it back on our frontier. We can always put it towards the back, or we can put it, somewhere in the middle, but the gist is ideally somewhere such that we can wait a little bit of time. So effectively the idea here is that you want to keep each table in memory such that, now I have a mapping from a host to the last time that I crawled that host. And so again, what we do is we just put the message back on our own frontier and take the next one. Now ideally, this is not going to involve a network call if our frontier, whatever that may be, and our actual processing node itself are co-located. It's possible that they could be on different servers, in which case that operation gets a little bit more expensive to throw something back on the frontier, and we would have to discuss that further, but in my ideal world, they don't require a network call. Okay, the next thing to touch upon is actually going to be fetching the URL itself. So the question is here, well, fetching is pretty simple. It's an HTTP request to a certain IP address. Can we do anything to speed this up? So one thing I have seen elsewhere just when researching this topic is that people will sometimes say, oh, maybe it's possible such that, we can partition our nodes such that, I have certain nodes in Europe that will only be accessing European URLs. I have certain nodes in America that are only going to access American URLs. And it seems that the general consensus on that is that it probably doesn't work just because the domain typically doesn't indicate where the URL is actually hosted, right? I might have a European domain, I might have a .uk, but at the end of the day, that doesn't necessarily mean the site is going to be hosted in the UK. So it's unclear. We might get some benefit from doing something like this, but for the most part, we're probably just going to have to eat the penalty of actually fetching the URL. Okay, moving onwards. Now we have storing results. So like all other things, when we make a write, we want to make a write to somewhere that is physically as close to our server as possible, right? And in this case, our writes are going to be pretty expensive because we're writing full HTML files, possibly indexing those HTML files and doing a bunch of other different things with them. So of course, we do want data locality wherever we can get it. Now, if our nodes are running in some sort of Hadoop cluster, it would be great if we could just export those to HDFS. That would make life super easy. That being said, I do find that a lot of people choose not to run their own Hadoop clusters. They're tough to manage, they're kind of expensive, and so a lot of the times, especially when we just need to store tons of storage, like in this scenario, we're probably going to be using S3. If we are, it would be great if we can make sure that our servers that we're doing all of these processes on are in at least a similar data center, right? So if I'm in US East 1 for my S3 zone, it would probably be really good if those EC2 instances that I'm using are also in US East 1. It is going to make the latency of writing quite a bit lower, and it's probably going to be cheaper than running HDFS. Of course, this is all going to vary on your specific use case, and you have to try everything out and benchmark it, but this is at least the assumption I'm operating under. Okay, let us go ahead and talk about pushing to the frontier, the last aspect of this problem. So now we've parsed our HTML document, we've maybe got 5 or 10 or even 20 different URLs that we know we have to go ahead and search next. What should we do with them? Well, the first question is, how do we actually want to model our frontier? And I'm thinking about this question from like a data structures and algorithms perspective, because at the end of the day, what we're effectively doing here is a graph traversal. And if we're traversing a graph, what algorithm do we want to use in order to traverse it? Well, one option is that we can do a depth first search, right? So when I basically access a website, I get the first link from it, I start traversing from there. All the other links, I'll deal with them later, and I just keep going and going and going. We could do that with something like a stack if we were able to build it. Recursion is kind of weird in like a distributed setting. I don't know how well that would work. But the issue here is, how do we really build a distributed stack, right? If I have this whole block of URLs to potentially fetch, and then, I got one guy adding to it from one process, I got another guy adding to it from another process, and then another guy adding to it from another process. I don't know, I kind of lose the idea of what a stack really is, because what was once the top of the stack is now not being popped. It just doesn't really make much sense to me personally. I think what does make a lot more sense would be a queue and performing a breadth first search. Again, I think the breadth first search is also a better option here, just because websites tend to link to themselves, and if they do tend to link to other sites that are on the same host, again, our caches are going to get a lot more hits as opposed to misses, and that can be really useful. So how can we actually go ahead and model a queue? Well, in a distributed fashion, there are quite a few things that do this for us. What does that? Message queues. The type of message queue that we're going to use still yet to be determined. We'll discuss that in a minute. But I personally think a queue makes a lot of sense for us here. Then the last aspect of this is potentially a priority queue. When I was reading through some of the literature on how to actually build a web crawler, I did see a decent amount of information saying that certain sites will actually choose to basically include a quality factor for every single potential URL that they're going to crawl, and then crawl them in some sort of preferential order. I'm not sure how practical this is going to be for just like a naive web crawler, but I suppose if you really wanted to, you could build some sort of in-memory heap and then do something like that and put that on a separate server. I don't think we're going to do it for this video. Let's keep things simple enough. I think that's probably a little bit out of the cards for a systems design interview, but it is still worth thinking about if it were relevant. Okay, so we've basically said now that our frontier is going to be a bunch of queues so that we can breadth first search all of our links. It's going to allow us to take better advantage of all of that caching that we're doing on our processing nodes. So the question is, what technologies do we want to choose? Well, a couple of things as always. If we are building a web crawler, we want to crawl the web reliably. We don't want things to fail, and if they do fail, we want them to come back up and restart from where they were. Additionally, it would be great if we didn't have to build all of these solutions for partitioning, replication, load balancing ourselves. It would be great if we could use some technologies that just went ahead and did that for us. And so, for this reason, I am going to continue my track record of being a Flink sexual, and I'm going to suggest that we use both Kafka and Flink. So as we know, Kafka is a log-based message broker, meaning that messages are persistent on disk. So if we go down, we can recover and start reading from the offset that we were at before. And then Flink, of course, is going to allow us to keep local state on that consumer that is fault tolerant. We can keep that state in memory. It's okay if Flink goes down, because occasionally it's going to be checkpointing, and when it comes up, it's going to bring up the checkpoint that it was last at. It's going to remember the Kafka offset corresponding to that checkpoint, and then it'll just start reading messages from Kafka because they're still on disk in Kafka. And so you can actually just build back up that state deterministically. In our case, we aren't going to have deterministic state because there's still external systems getting involved. Our DNS results can be modified from one run of a Flink thing to another, but it is still going to make sure that we do end up actually crawling every single link that we're trying to crawl. And so another nice thing here is that, if we have a Kafka instance, we have a Flink instance, well, we don't really want Flink to be having to make a network request to Kafka all the time, or at least if we do, we want it to be as fast as humanly possible. So ideally what we can do is just co-locate these two either on the same physical server or in the same data center, and that way we can ensure that latency is as low as possible. Because if you recall, there are going to be a lot of times where we're trying to crawl a website and its robots.txt is going to say, hey, you can't crawl this yet, and then we want to go, hey, Flink, it's time to re-enqueue on your own Kafka queue, and we want to make that as fast as humanly possible. So again, like I mentioned, full replayability. We know we're not going to drop any links. And of course, partitioning is super easy to do with Kafka. It's got Zookeeper under the hood, and it can just go ahead and do all of that for us. We just have to provide it with a partitioning key, which, as we mentioned, is going to be the host of the URL. Of course, all of the rights to S3 can be idempotent, right? Because at the end of the day, if we take some HTML content and we set its URL to just be the hash of it, then if we write it again, we're just going to overwrite whatever content was previously in S3 there. So that's fine. This is all good and well. We need basically any external interactions from Flink. If we're going to another system, we want that to be idempotent because of the fact that we're going to have to replay things sometimes if our Flink instance goes down. And then, of course, the really, really nice thing about Flink is that we can basically use all of that internal state and the ability to cache things in memory in order to do caching of both DNS results and robots.txt results per host, which is going to be super nice for us. So let's go ahead and talk about our final design. For our web crawler right here, let's imagine we've got 3 separate nodes over at the bottom. These guys are going to be doing all the processing. Again, I thought it was very important that both the frontier and the processor are at least in the same data center, but ideally co-located. So effectively, we've got these co-located Kafka queues and Flink instances, and they're going to parse a bunch of URLs, and once they do, now all of a sudden we're sending our URLs back to the load balancer. The load balancer is going to say, hey, wait a second, some percentage of these might go back to you, some percentage of these are going to go to this guy, some percentage of these are going to go to this guy, and then they can just keep processing, and that's all going to be based on the host name. Now, of course, once we're processing something, if the data isn't cached, we're going to have to pull from our DNS into our Flink instance. We are going to have to read from the Redis cache in order to see whether or not we've processed this HTML before. And then we're also going to have to write back to the Redis instance to basically say, hey, I've processed an HTML document, here's its hash, you should hold on to this thing. It's going to have a single replica, or as many replicas as your heart is content with. And of course, we also have S3, which is ultimately going to be the sync of all of these operations. Now, I did mention that we don't necessarily need to have these Redis things. We could do like a CRDT of all the hashes that is local to all of these nodes right here. But at the end of the day, I do think that Redis keeps things pretty simple. Of course, if our system was too slow, we could always try switching to a CRDT implementation and seeing if that helped us out at all. Anyways, guys, I hope you guys found this video informative. I am now going to sign off as my throat is hurting me a little bit. I wonder why. And I will see you all in the next one.